Hi class, welcome to 3.2. So, logarithmic functions. So, as we already talked about the exponential functions, you have seen what the graph of an exponential function looks like. So let me draw one more really quick for you. Whether it's an increasing or a decreasing exponential function, what we say is that an exponential function is 1-to-1, meaning that it would pass the horizontal line test, of course, as well as the vertical line test, which makes it a function. But 1-to-1 means it also passes the horizontal line test. So as you have learned in algebra, that if a function is 1-to-1, it's going to have an inverse. So how do I find the inverse of a function? Okay, so something that undoes it. So just as an example, a square and a square root function undo each other, because if you square and then square root the value, then they just go away, right? So whether you square a number and then you square root it, that's what makes them cancel each other out. In any order you want to do that, yes? So that's why the square and the square root functions are inverses of each other. Good. So really quick, how do we find an inverse? Well, you've learned that what you do is you rewrite f of x with a y, and then what you do is you swap x and y, and then you're trying to solve for y. So how are you going to solve for y? Well, nothing that we might have done so far could solve for an exponent. So you might remember again from your algebra classes that what solves for an exponent is a logarithm. So in that case, y is going to equal to the log with base b of x. Okay, so that's the inverse function of the exponential function. And you might hopefully also remember how we write inverse functions. You put the -1 to the f of x. That's the notation for an inverse function. So what does this symbol mean again? Log with base b of x, okay, is really the logarithm with base b of x. That's how we read it. And what it equals to is equal to the exponent to which you have to raise b in order to get x. So what does that mean? So log with base b of x is this y value. Where did we see this y value before? We saw it in this exponent to which you had to raise the number b in order to get x. Okay, so sure enough, every time we solve for a log, or what the log does give us is an exponent. Every time we solve for an exponent, we use a log. So that's what they're equal to each other. You need to find an exponent, you use a log. What is a log? An exponent. Okay, so just to practice really quick what it all means, what is log with base 2 of 8? So that simply means to find the exponent to which you need to raise this number 2 in order to get 8. So sure enough, you guys know that that exponent must be 3, because 2 to the power of 3 gives you back the 8. Okay, let's try one more. What's log with base 5 of 25? So log with base with 5 of 25 is, again, what exponent do you need to raise this 5 to in order to get 25? So sure enough, 5 squared equals to 25. And you can try a few more. Here, what about, I have on the notes, log with base 7 of 1 over 7. Well, log with base 7 of 1 over 7 means, again, what exponent do you need to raise the 7 to in order to get 1/7? And sure enough, that's a -1, right? A negative exponent makes things go on the bottom. What about log with base 9 of 3? So what do you have to do to 9 in order to make it a 3? And I don't mean -6, and I don't mean divide by 3. What I mean is, what kind of exponent do you have to raise the 9 in order to make it a 3? And sure enough, it's a square root that you have to apply, and a square root is a 1/2 exponent, as we went through so many times in the last lectures. Okay, so there's that. Now, a simple problem like this, log with base 2 of 10, not quite sure how we're going to figure it out because 10 is not a power of 2. So sure, 2 to the third would get me as far as 8. 2 to the fourth would get me as far as 16. So my guess is that between 10 being between 8 and 16, maybe the answer is about I'm sorry, not 2 because to the third is 8, maybe 3.2-ish, 3.3-ish, something like that, maybe 3.3 more like it, okay? So, yeah, but we definitely need the calculator for this. Okay, so what we need to do next is look at logarithmic functions, find the domain, the range, and what the graph looks like. So here is a logarithmic function, log with base b of x. So remember the b to the power of x that we had in the last section, the exponential function? Well, this is a log with base b of x. So same as in the exponential functions, the base should not equal to 1, and it should be positive. Again, for the same reasons, the inverse of an exponential function is a logarithmic function. The same rules for the bases have to apply to both. Now, what you have learned, and let me draw an exponential function one more time for you. Let's say 2 to the power of x, which we drew last section, somehow looks like this. So if the base is more than 1, then the exponential function looks like this. You've learned a few things. So what you've learned about exponential functions, what we talked about in 3.1 is that the domain of an exponential function is all real numbers, but the range is 0 to infinity. Yes, so the y values that you get out of an exponential function are only going to be positive. So this graph lives above the x-axis. Yes, as a matter of fact, the x-axis is what we would call a horizontal asymptote for it because the graph gets closer and closer to this axis. Now, what you've also learned is that a function and its inverse, because they swap x's and y's, they're also symmetrical to each other about this line y equals to x. So a logarithmic function will in fact look like this. So a log with base b of x would have this type of graph if b to the x has this graph. So they are inverses of each other, symmetrical to each other about the y equals to x line. So sure enough, if you have an exponential function and you raise it to the power of 0, the answer will always come out to be 1. So no matter what, base to the power of 0 is equal to 1. So what would be a log with base b of 1? Well, the answer is 0, right? These numbers are being swapped. So I could have asked you that question up here just fine. What's log with base 5 of 1? Yes, so in other words, what exponent do you have to raise this 5 to in order to get a 1? And the answer is definitely 0, right? Because 5 to the power of 0 is equal to 1. And that would be the same answer no matter what base I would have put here. 15 to the power of 0 is 1. 22 to the power of 0 is 1. It doesn't matter. So they all go through this point, okay? So as you see, and as you probably remember also from your algebra classes, a function and its inverse, because they swap x's and y's, they also swap domain and range. So the domain of an exponential function is 0 to infinity. The range is all real numbers. That's very important because what that simply says is that you can only put positive values inside the log, as you can see from this graph, right? So the domain, the x values are just on the positive side, yes? Whereas what's the range? It's all real numbers, right? Goes up and down. And as a matter of fact, as I just said, about y equals to 0 is a horizontal asymptote to the exponential function. So x equals to 0, swap x's and y's, x equals to 0 is a vertical asymptote to the logarithmic function. Okay, log with base b of x. Okay, so it's a vertical asymptote. The graph gets closer and closer to it. Okay, so what we want to do next is just review a whole bunch of rules of exponents. just to review a little bit. So, if you guys can see, properties of logs, they could come in handy. Log with base b of a product turns into the sum of the two logs. Log with base b of a quotient turns into the difference of logs. If you have inside a log a number with an exponent, that exponent comes up as a coefficient, and it's the product of them, okay? And then the inverse property, which are important, same as a square and a square root undo each other because they are the same power, right? Or a cube and a cube root. Log with base b and a power of b and a base of b are going to cancel each other the same. So log with base b of b to the something is always equal to x. So they will also cancel each other out going backwards. A base of b to the power of log with base b cancel each other out and leaves you with just an x, right? So again, that's the equivalent of what? A cube root and a cube undo each other in any order you want. So you first take the cube root and then the cube, they're gonna cancel out. You first cube and then take the cube root, they're gonna cancel each other out. Okay, all right, so let's use the properties of logs to write as a single log. That's gonna be helpful. It will also be helpful to expand, sorry about that. So write as a single log. Okay, so what would be log with base 2 of 5x minus log with base 2 of x? So sure enough, in all these properties, the bases have to be the same. So yes, if you have an expression like this, what we get to do is log with base 2 of, we just simply divide the insides of it. So 5x divided by x, that's just a 5. That's going to help us greatly when we want to take derivatives of logarithmic functions. And if you could simplify this together, look at that. In fact, the x's went away. What would be the derivative of log with base 2 of 5? Well, log with base 2 of 5 is a number. The derivative of just the number with no x is 0. So you wouldn't even have to do anything. Yes. So it definitely is helpful if we can simplify. Log with base 7 of 3 plus log with base 7 of 9, what do you get to do with these logs? Well, you get to multiply their insides, and you get log with base 7 of 27. Let's see, what about this problem here? 3 log with base 5 of the cube root of x. So what do you get to do with this? Well, this 3 comes up here as an exponent according to the last rule. So it got put up as an exponent, and just as we said, what does a cube and a cube root do? They cancel each other out, okay? So this could be very helpful later on because you don't want to deal with so many combinations of functions, right? Compositions of functions. If you can make the problem shorter, then yay, you can get it done. Okay. So natural logarithmic function and the common logarithmic function. So we talked about the natural exponential function in the last section. So what did the natural exponential function look like? The natural exponential function was simply the exponential function with base e. Now, of course, just like any exponential function, it will have an inverse. What is the inverse of it? Well, the inverse of this exponential function is 1 that has a log with base e. Yes. Now, it turns out that's the only one that we'll be dealing with in applications that come up in our business calculus, because the only exponential function that we'll be dealing with is the natural exponential function. So that's the one to pay attention to. So we have a new name for this. The log with base e of x has a special notation, and it's called ln of x. So that's the natural logarithmic function. So now finally, I'm sure you get to see on your calculator the ln, and you might have looked for log with base 2 and couldn't find it, but that's because it's not there. But the ln button is there, and it's a log with base e. Now another common logarithmic function is, again, There is no common exponential function. Maybe there is, but people don't really use it. But this logarithmic function with base 10 is also very commonly used. So just same as the square root is the most used root, and then we got lazy and we stopped writing the 2, yes? All the other roots we have to write the index, but for the square root we don't. Same with the common logarithmic function, we don't write the base. So if you see a log without a base, it always means a base of 10, okay? So we don't write it anymore. Same as you see a root with no index on it, you always know that that's a square root, okay? All right, so finally we get to turn this into a change of base formula, or want to figure out how am I going to use my calculator to come up with that log with base 10, or log with base 2 of 10, yes? So how would I be able to find the answer to this problem? So that's the change of base formula, and it says that you can take a log with any base of any number and turn it into a new base. It's the log of the new base of what's inside divided by log of the new base of the old base. So basically, what this translates to, you have 2 buttons on your calculator. You either have a common log button or you have a natural log button. So you get to use either one. Let's say you use the ln button, so it's ln of 10 divided by ln of the old base, which is 2. So put that in your calculator and you're gonna come up to about 3.32. So that was very close to our guess for it. Now, of course, that's the same thing you get to do if you want to grab the common log button, then that you will get the same answer, and try them both, and hopefully you'll get a 3.32 for both those answers, okay? So these are the 2 logarithmic functions that you can use in your calculator. So, and then you can use the change of base formula to figure out a log of any other base, right, in terms of it. Okay, so let's see what else. Okay, solving equations. Well, that's definitely helpful. So we will be dealing in the next expressions, or in the next applications, with all sorts of exponential logarithmic functions, and we're going to need to solve them. In other words, we're actually going to want to find that exponent mostly. So we will mostly be using solving exponential equations. And how do you solve an exponential equation? Well, kind of the same idea. How do you solve a radical equation? Well, to solve for a square root, or to make a square root go away, well, what we're doing is squaring both sides, yes? So that's because they're inverse functions of each other. So if you want to solve this exponential equation, you have to apply its inverse. And what's the inverse of a base 2 exponential function? A log with base 2. So all you have to do, I'll write over it. All you have to do is apply a log with base 2 on both sides of the equation. So what does log with base 2 of 2 do? They cancel each other out, right? As long as I use the same base. So it leaves me with an x. So x is equal to log with base 2 of 5. Now, how do you find what log with base 2 of 5 is? You put it in your calculator and you make a change of base, right? So that will be ln of 5 divided by ln of 2, which is about some kind of value, I don't know, 2.3-ish, I guess it comes up to be. So there's your answer now. So easily done. Now, in fact, I'm going to solve this problem also a little bit differently for you. And let's say I'm starting with the same 2 to the power of x is equal to 5, okay? And I want to get to that x. Now, sure, I use the log with base 2 to make that base of 2 go away. However, I don't know what log with base 2 is. I need to change it in my calculator, so I turn it into an ln. So the question is, could we use a natural log from the beginning? Sure enough, right? Can I cube the square root? Yeah, if it's helpful, why not? I can do whatever I want to both sides of the equal. Now, this natural log won't cancel the 2. But what the natural log will do is will force the x to come out. Remember this property of log right here that says if you have inside of any log a number to an exponent, what does that exponent do? It comes up as a coefficient, yes? So that's the property we'll use here. So what that log does, it makes this x come up front as a coefficient. So it's an x times ln 2 equals to ln 5. So what's the last thing to do to get to x? Well, divide by ln 2. So is this the same exact answer that we got before? Sure enough, yes, and we didn't need to use a change of base formula. Okay, so let's see if we could solve this problem, next problem, a little bit faster. Again, maybe it's about some quantity that starts at 2,000, grows at a rate of 5% per year, so the base is 1.05, and we want to get to this time, right, that it will take to become 27,000, right? So how am I going to solve this equation for t? Well, the first thing that I could definitely do is get rid of that 2,000. So I can divide both sides by 2,000, great. And then I'm left with a 1.05 to the power of 4t is equal to something, and that something is 13.5. Okay, and now I need to get in here to this exponent. So how do I solve for an exponent? Well, I have to use a log. And same thing, I could use a log with base 1.05 to make this go away, but then I need to use a change of base formula. Or I can apply a natural log from the beginning on both sides of the equal. So what does that natural log do again? The natural log, now that this quantity is inside the log, this 4t exponent will come up as a coefficient. Okay. And then I need to solve for t. What do I do to get t by itself? Well, t is multiplied to both 4 and this natural log. So I'd say we should divide by both, right? It's multiplied to both. We should divide by both and make them go away. So t is going to equal to, well, put this whole thing in your calculator and you're going to get about 13.3. Something. More decimals. All right. Let's see. Let's go through this really quick. This one's a good one because the base is already e. So if I apply the natural log on both sides of the equal, what's going to happen? ln and e being the same base or having the same base will cancel each other out. So I get that 3x is ln of 117. And to get to x, all I have to do is just divide by 3. Okay, put that in your calculator, you get about 1.59. Now, I'm sure you're asking yourself right now in your brains, well, how many decimal places do I need to give? Or could I leave my answer just as ln of 117 over 3? And the answer is, depends on the question, yes? If I'm going to say how many years or how many months or whatever does it take for an amount to grow to a certain value, yes, let's say 117, and you give me that the answer is ln of 117 over 3, I'm still none the wiser of how long that might take, yes? So an approximation definitely gives me a better idea. How many decimal places you're giving me is really up to you. 2 decimal places is always a good choice. If you want to put 3 decimal places, that's fine, but it really doesn't matter. Okay, so let's solve this problem. Same thing, I'm going to divide by 100 first. And I'll get an e to the negative 0.02t is 0.4. And how do I now get in the exponent? In other words, how do I get rid of this base? Well, I get rid of this base, or I solve for an exponent by using a log on both sides. So ln of e cancel each other out. And ln of 0.4 is something out of your calculator. what I still need to do is divide by negative 0.02. Okay. So t is going to equal to about 45.8 apparently. Okay. And again, we're going to use all these tools just in a bit when we solve some word problems. Okay, so remember what I just said, that we will be concentrating only on the natural logarithmic function, as any exponential function can be actually rewritten as a natural exponential function. So if you remember, I know I threw those papers somewhere around here. I don't know, I put them, but the point, I know I put them somewhere here. There you go. Is this it? Okay, give me a sec. At the end of the last section, I said that we can change any exponential function into 1 with base e. And so 2 to the power of x is e to the something x. And how do I find that something? Well, turns out that something is 0.6931. And I had you verify that this answer is just about a 2. And sure enough, if you put in a calculator, you probably got 1.999, about 4 nines, yes? So yeah, I just need the x on top, but I could rewrite this exponential function with a base of 2 into 1 with base e, and it has like a PERT formula, e to the rt, yes? So how do I rewrite 2 to, where do I get that number from, right? So 2 to the power of x is going to equal to e to the what? Yes, so how do I find that y value? Yes, out of it. Okay, so sure enough, all I want to do is solve this equation for that y. So all I want to do is put a natural log on both sides. Yes, I want to get that exponent. What is that going to look like? So I'm going to get rid of this base of e. And I will get that this y that's going to end up being at the top of the e is ln of 2 to the x. Great. What can I do? Well, I can take the x up front, x times ln of 2. And now put this in your calculator and tell me what ln of 2 is. Well, sure enough, ln of 2 is the number that I gave you, 0.6931. Okay. So in other words, what? To rewrite this, 2 to the x is an e to the what y value? 0.6931x. And then again, why? Because 2 is equal to e to the 0.6931. That's really, by the way, exactly as I said, that, right? E to the ln of 2 is really 2, because e and ln will cancel each other out, then we just give you a 2, okay? So just because, as I said, we will be dealing with only natural logarithmic functions, I rewrote here these properties to make them look familiar. So when you'll have, again, we went through the properties of log with any base, but of course they apply to a natural log function as well. So whenever you see an ln of a product that splits into sum of the two logs, or backwards, a log plus a natural log plus another natural log, you get to multiply the insides. The minus means you divide them. An exponent gets thrown in the front or put back in, depends which way we want to go. ln and e will cancel each other out, and we'll just get you an x. E to the ln will cancel each other out, and we'll get you an x. Also helpful, just as we had before, any log of any base of 1 always equals to 0. And ln of e is equal to 1. Why? Because ln and e cancel each other out, right? That's the power of 1 right here. Or in other words, e to the what power gives you an e? Well, the answer is 1, yes? So log with base e of e is what? So what exponent do you have to raise e to get e? Well, the answer is a 1, right? Except for we write log with base e just as an ln. So we'll take a break for now. Long video.